In this video, we will do a short review about derivatives. Let us consider a function. This is the independent variable t, and let's suppose that we have here y equal to f of t, and let's suppose that this is the graph. Let's suppose that this is a point t sub 0, and this is y sub 0 equal f of t sub 0. The problem that the derivative solves is the one of finding the slope of the tangent line. Then the derivative at t sub 0 will provide the slope of the tangent line. That means that the equation of this line is y equal to y sub 0 plus the derivative at t sub 0, this is the slope, times t minus t sub 0. This is the equation of the line. How do we define derivative? This is the definition. The derivative at t sub 0 is equal to, we use a limit. The limit when h goes to 0 of f of t sub 0 plus h minus f of t sub 0 over h. That's the definition. And for example, if we consider the function f of t equal t squared, and we want to compute the derivative, then the derivative at some point t sub 0 will be the limit when h goes to 0 of f of t sub 0 plus h would be t sub 0 plus h squared minus f of t sub 0, which is t sub 0 squared over h. And this expression here, let me just do it here, this expression reduces to t sub 0 squared plus 2 times t sub 0 times h plus h squared minus t sub 0 squared over h, but these two cancel out, and here we can factor an h and get h times t sub 0 plus h over h. That means that this is the limit when h goes to 0 of 2 times t sub 0 plus h, and when h goes to 0, this goes to 2 times t sub 0. That means that the derivative, we write that the derivative of the function t squared over t is just 2t. But something that is going to happen is that we are not going to use this definition. It will be too long. We're going to be using some properties. And then let's say what properties we will be using to compute derivatives. We have very easy to prove that the derivative with respect to t of a constant is just 0. The derivative with respect to t of t to the n is n times t to the n minus 1. And we did a case in which n is equal to, we did that the derivative of t squared is 2 times t, but this one works for any n is a real number. For example, the derivative of a square root of t, n would be 1/2. Then we have another property, the derivative of cosine of t is negative sine of t. The derivative with respect to t of sine of t is cosine of t. The derivative with respect to t of e to the t is e to the t. The derivative with respect to t of arctangent of t is 1 over 1 plus t squared. And the derivative with respect to t of natural log of absolute value of t is 1 over t. We have these properties that goes through the basic functions, and we have some properties that says that if the derivative with respect to t, if we have a constant times a function, let's say f of t, then this is just the constant times the derivative of f with respect to t. If the derivative of a sum of two functions, we have f of t plus g of t. It's just the derivative of the sum of the derivatives. The derivative of a product, we have like f times g. Then this is f times the derivative of g plus g times the derivative of f. The derivative of a quotient, f over g. This is just f primes times g minus g prime times f over g squared. And this is one of the most important properties, the derivative of the chain rule of a composition of two functions. It is f prime evaluated as g of t times g prime of t. Let's practice this one and we were going to view it in a slightly different way. Let's suppose that we want to compute the derivative with respect to t of 3t squared plus t to the power of 20. Then the property says that if we can do a substitution, if we can make, for example, u equal 3t squared plus t, in such a way that this is the function that we want to take the derivative. When we do this substitution, this is going to look like u to the 20. Then here we have two functions. The substitution that we are doing, u equals 3t squared plus 20. And with this substitution, this function looks like a function in terms of u. Then the rule says that the derivative of this function, let's call this function y of t. It says that the derivative of y with respect to t is equal to the derivative of y, but in terms of u, times du with respect to t. This is the same chain rule, but look how natural it looks. It's like this du cancel out. Y view as a function in terms of u is u to the 20. Then this is 20 times u to the 19, and the derivative of u with respect to t is 60 plus 1. That means that the derivative of this function, dy with respect to t, is just 20 times, now we change the u, 3t squared plus t to the power of 19 times 60 plus 1. This is one way that is going to be useful to visualize the chain rule. Let's do another example here. Let's forget about this. Suppose that we already know these ones here. Then if we have something like we want to compute the derivative, y is e to the 3t squared plus sine of t. Then if we make u equal to 3t squared plus sine of t, then the function y is going to look like e to the u. Then the chain rule says that the derivative of y with respect to t is equal to the derivative of y with respect to u, the way it ends up being after we do this substitution, times du dt. Notice that the u cancel and we get like the same expression. But the derivative of dy with respect to u is the derivative of e to the u, following this property, is e to the u, and the u dt is 6t plus cosine of t. That means that the derivative of y with respect to t would be e. We replace u back to this, is 3 to the t squared plus sine of t times 60 plus cosine of t. Sometimes we're going to do derivatives of functions that have some constants. We don't know the constant. Let me just practice two of them. Let's suppose that we have a function that looks like a t squared plus bt plus c plus d cosine of t plus e sine of t. What is the derivative of this function? Then we are assuming that the a, b, c, d, and e are constants. Then we have 2at plus b plus the derivative of c is 0 minus d sine of t plus e cosine of t. Notice that we can talk about the derivative of the derivative. That's called the second derivative and is denoted like this. In this example, it would be 2a minus d cosine of t minus e sine of t. Let's finish with one last example, something that we will be seeing later. If we have like e to the 3t times cosine of 4t. Let's compute the first and second derivative of this function. The first derivative, we have to do the product rule, but to do the derivative of this, we have to do the chain rule. We have to think about u being equal to 3t, and then we have like this is e to the 3t times 3, the derivative of the first function, times the second, plus the derivative of the second function. We have to do the chain rule here, and we end up with minus 4 sine of 4t times e to the 3t, and this is it. This is the product rule for this. And then the second derivative will be, here we have to do the chain rule again. The derivative of the first function is going to be 3 comes down, and then we have 9 e to the 3t cosine of 4t, and then the derivative of the second function would be minus, that is a 4 and 3 minus 12 e to the 3t sine of 4t. Then we continue with this one. It would be minus the derivative of the first function, which is 16 cosine of 4t times e to the 3t, and then the derivative of this one times this will be minus 12 sine of 4t times e to the 3t. This would be the second derivative and the first derivative of this function. I think I will stop here.